Welcome everyone and good afternoon. I'm part of the industry specialist team, and in that role, I'm actually focusing on new and upcoming technologies. So one of those technologies is the capability to predict the MVH performance of virtual vehicle prototypes, more specifically hybrid virtual vehicle prototypes. And for today's session, the topic that we're going to discuss is an important part of that kind of prediction, which is trying to obtain accurate mount data to represent the boundary conditions between our components. First, just a quick recap of the challenges in mount stiffness characterization. So what are the typical things and problems that we try to solve there? And then the main topic for today is to discuss two of the what I call advanced methods, but mainly methods that allow us to get more accurate and more useful mount stiffness data for different purposes, among others, MVH prediction in these virtual prototypes. And at the end, very shortly, I'd also like to discuss about nonlinearity in mount models, more specifically due to preloads. To get started, first, let's just consider a very typical situation that you might find in a vehicle, which is basically what the function of the mounts is. So your mounts are existing between different components of your vehicle. For powertrains, like here, you can see that you have one isolation stage between your powertrain and your subframe. And then the subframe is also softly coupled to the vehicle. So any operational loads that the powertrain is generating is filtered at these two isolation stages before it reaches the vehicle. So obviously, how we select or which mounts that we select to put in between those components is going to have a very big impact on the overall MVH performance. The softer those mounts are, the more effective they will decouple the powertrain loads from the vehicle. So on the one hand, we want to have very soft mounts for MVH performance, but soft mounts also give quite weak boundary conditions for those components. A stiffer mount might actually be better when it comes to control. When we think of, for example, fluctuating torque situations, if you're driving your vehicle very sportively, that fluctuating torque might cause some wobble of the powertrain that gives you other MVH issues down the line. We want to make a very fine balance between isolation and control when we select our mounts in this situation. Now, the difficulty is that mount stiffness is something that is not just a fixed quantity. We call this dynamic mount stiffness because it depends on the frequency of the excitation. And that also means that we need to know which stiffness we are dealing with for our mounts for the entire available range for our loads. And nowadays, with more and more electric powertrains being more popular, even in hybrid vehicles, of course, with electric powertrains, the frequency ranges we consider are much higher than they used to be. So it means that also the mount models that we need, the mount stiffness data we need, needs to be available up to higher frequencies. What we also see at higher frequencies is that the complexity of the coupling starts to increase as well. So instead of only considering XYZ transfer, it starts to become important to also consider how rotational loads are being transferred from one component to the next. Yeah, we ask a lot from our mount models essentially, but it's not that easy to get accurate mount data. One reason is what I just mentioned, it's dynamic mount stiffness, so there is a dependency on the frequency range. But mounts are difficult to model because they have a ton of operational dependencies in general. One very important one that I think many people will be familiar with is preloads. If in operation our mount gets somehow compressed or is in tensile condition, that compression will change the mount stiffness of the mount itself. And as you would expect, the more compression we put on the mounts, the stiffer the mount is going to become. Another operational effect is the temperature. If your powertrain, in this case, is getting hot during operation, it might heat up the mounts, and as the rubber is getting warmer, the stiffness tends to decrease. So that is another variability, let's say, on the mount model. One last notable dependency is degradation, which simply refers to the fact that rubber tends to exhibit creep over time. And basically, the older your mount is, the more creep and the stiffer the mount is going to become over time. So maybe a new vehicle that is fresh from the factory has good MVH performance, but due to creep, it might eventually still lead to some MVH problems down the line. All of this is just to say that there is a need to be able to measure and obtain mount stiffness in different operating conditions so that we can basically map all these dependencies versus frequency and other operational dependencies to build up these mount models. And I would say that traditionally, the typical way to get this kind of data is what you would essentially find on a data sheet. If you're buying your mounts from a supplier, the mount stiffness that would be stated on that data sheet will most likely be measured on a hydropulse test bench. So this is essentially a hydraulic bench where we can apply some hydraulic force pulse to the mounts, and then we just measure the response of the mounts to get the dynamic stiffness curve directly. This works quite well, and it's actually also compatible with static preload. So we can apply a constant preload with the hydraulic system and then put the pulse as kind of an AC component on top of it to map the preload dependency. But if you look at these results, you can see that there are some limitations when it comes to these measurement methods. The first one that I want to point out is the frequency range. This does depend on the specific hydraulic test bench in question, but in general, what you will find is that this measurement method is limited to a few hundred hertz at most. Let's say anywhere between 100 and 500 hertz would be typical, and not really any higher than this. That's already a problem because for a powertrain, maybe 2000 hertz or 3000 hertz could be roughly the frequency range where we want to do structure-borne noise predictions, especially for electric powertrains, and we're not going to have enough data here to cover that frequency range with these test methods. Now, having said that, I will say that I've recently seen some specialized benches being developed which can go into the kilohertz frequency range. So there are some benches that can go beyond what is stated here. But even then, there is a second problem with the data that we're obtaining here, and that is that this is a direct measurement method that only gives you the three principal degrees of freedom for the mounts. So only the X to X, Y to Y, Z to Z coupling that the mount provides, which means that we're missing the information on the rotational coupling. So how do moments transfer over that mount from active to passive? And what we're also missing is how the different degrees of freedom are coupled to each other. So X to Y, Z to Y, we don't really have a way to obtain that data on this bench. Again, for low frequencies, the frequency range where these hydraulic test benches work very well, this probably isn't that much of a problem. Like XYZ is probably defining the majority of the influence of that mount. But again, as we go to higher frequencies, we would like to get more coupling complexity. That is the central question that I want to ask, but also answer in this session, is how we can actually measure higher fidelity mount models that allow us to go into the kilohertz frequency range, but also include all these coupling degrees of freedom. And eventually, I'll also explain how those methods can also be made compatible with nonlinear dependency so that we can create a more complete map of our dynamic stiffness. The first method that we're going to be looking at, and the one we'll be studying most of the two, is called inverse substructuring. And before I explain what inverse substructuring is or how it works, I just quickly want to introduce you to another technique that will be very important in the implementation of this method, which is called virtual point transformation. The idea here is that if we have a subframe in this case and we want to characterize one of the mounts on the active side, so this is a suspension connection, if we're interested in characterizing these mounts, we're going to need to measure some data probably at the center of that mount. And a problem there is that, as you can see from the instrumentation setup that I'm using here, is that it's generally impossible to measure acceleration at exactly the center of a mount or to put an impact hammer or a shaker at that center. We need an indirect way to obtain, in this case, FRF data at the center of that mount. And the way that we're going to do that, we're going to instrument around the mount. So I have 3 triaxes here, and I think about 9 excitation positions around the mount. And we're going to perform a geometric reduction of that measured data to the center in order to get data exactly in this, what we call a virtual point. Now, an added benefit of doing this is that during that reduction step, because there is an offset between where the excitation and response is measured compared to this virtual point, we can at the same time, for free, estimate rotational degrees of freedom at that center. VPT, if you really want to boil it down to the essence, is a method of obtaining, in this case, FRF data at some inaccessible location, like the center of our mounts, and including some quantities which are otherwise difficult to measure, like rotational degrees of freedom. Now, the only thing that is quite important in VPT is that this is a geometric reduction. So that means that implicitly we're making an assumption, and that is that there is rigid behavior between where we perform the measurements, like this impact position, and where the virtual point is. You'll find later during the case study, as we go through this step by step, that the rigidity of the structure on which the measurements are performed are likely going to define the frequency range where the method can be applied. So the more rigid our structure is, the higher the frequency where we can apply this VPT. VPT is VPT, and that's not yet anything to do with mount stiffness estimation. So let me explain why this is relevant as we go through these inverse substructuring methods. For that, consider just this simple mount here, which has on the top an active side and on the bottom a passive side. We're going to represent this mount by a 6 points on active and passive side. So we're saying that the input has 6 degrees of freedom. The output also has 6 degrees of freedom. And that means that a full dynamic stiffness characterization of this mount would be a 12 by 12 matrix. So it is an input stiffness, an output stiffness, and then a transfer stiffness, which assuming reciprocity is just equal on input and output sides. Now, what is key in inverse substructuring is that we're going to make an assumption on how this mount works in order to simplify our lives quite a lot, as you will see. So this is really the key to having an efficient and easy way to estimate mount stiffness, is that we can make some assumptions which are reasonable up to a certain frequency. That assumption is that we can model our mounts as essentially being an EverF, which means that the mount itself has no or negligible mass compared to the structures that it's trying to couple. And there is no significant cross-coupling between the degrees of freedom. So the X stiffness is much more important than the X to Y stiffness would be, for example. And under these assumptions, I'm not going to show the mathematical derivation, but there's papers I can refer to if you're interested. But what is quite important is that when we make this assumption, we can actually show that this full 12 by 12 dynamic stiffness matrix can be represented using only the off-diagonal terms. So only the transfer parts from active to passive or vice versa is what we need to define these mounts. Maybe you're asking yourself, why is that important? And I'll explain why that is important as we go through the process of applying inverse substructuring step by step. The measurement procedure that we're going to follow now is we are going to start by attaching these rigid jigs or these crosses as they are shown on the image to the active and passive side of our mounts. So the purpose of these crosses is that they need to be as rigid as possible because we're going to apply VPT to that later on. What we're going to do then is we're going to take this assembly of mounts with the rigid jigs and suspend it in free using just some simple bungees here. And what we're going to do next is we're going to measure with virtual point transformation an EverF matrix at the center of our mounts. And this is going to be a 12 by 12 matrix. So it is at and between the active and the passive sides of that mount. So it's a 12 by 12 EverF matrix. And if you look at what an EverF is, so it's written here, EverF is essentially response over force, like G over Newton. And what we're looking for mount stiffness is something that is typically represented as force over response. So more something like Newton per millimeter would be typical. That means that we need to invert our EverF matrix. And this inverted EverF matrix is actually representing the dynamic stiffness, not just of the mounts, but also the jigs on the active and passive sides. So you can see that by making this assembly, the active sides is the mounts dynamic stiffness plus the jig dynamic stiffness. So it's kind of made a modified assembly here. We're not interested in the jig dynamic stiffness. We are just interested in the mounts dynamic stiffness. And this is actually where that assumption from before comes in, because we know that if we can make this assumption that the mount behaves approximately as an EverF, that we can represent that dynamic stiffness matrix using only the off-diagonal terms. And you'll notice that the transfer part of the mounts is unchanged by putting the jigs on top of it. That's kind of the core behind this inverse substructuring, is that as long as this EverF mount model holds, we can represent the dynamic stiffness of the mounts using only the off-diagonal terms, which don't have any jig influence on them. And that is also the main reason or use case for inverse substructuring, I would say, is that this is a very accurate dynamic mount stiffness estimation technique, but it's also a very fast method that in the sense that it doesn't require any measurements on the jig. You can basically put whatever jig, whatever rigid structure that you can build on the active and passive side, and you don't need any additional information on those jigs to get the dynamic mount stiffness. Another benefit here is because we're using VPT, the rotational DOFs, they actually come for free as part of that transformation. Instead of estimating XYZ dynamic stiffness, this is going to be a full 6x6 transfer stiffness that we're estimating at the end. And the frequency range for VPT can be quite high, so easily in the kilohertz range. In reality, as you'll see later, it really depends on the rigidity of the jigs that you use. So that's the bottleneck, if you want, for the frequency. Now, on the negative side, there are always drawbacks and trade-offs in engineering. So the main thing here is that the FRF mount model excludes mass influence. And maybe at higher frequencies where your mounts cannot be assumed to be not modifying the assembly in some way, that assumption might not be entirely accurate. The mount is actually only providing a boundary condition between the components. It's not acting as a structural element of the assembly as such. So that might limit the high frequency validity. And another thing is that this measurement is done in free. So we suspend the assembly with these bungees, and that means that by default, we cannot apply any preloads. So right now, this is like a static mount stiffness at 0 Newton preloads. I'll talk a bit more about preload at the end of the session, but for right now, this is going to be a limitation for this setup. I'd like to jump into a demonstration in the software, also to show you step by step as we go through this with an actual case study, show you some sample data and what you can expect from these methods. What I want to mention before I go into the software is that virtual point transformation and inverse substructuring are available both in what some people might refer to as TestLab Classic, but also in our newer generation platform, which we call TestLab Neo. I will be using the Neo workflow for this, and the reason is that this Neo workflow has a few extra additions available that really will make a difference in the frequency range that we can achieve with this method. So more specifically, CAD-based virtual instrumentation and some algorithms that help you automatically select the best data to increase your frequency range are only available on this Neo platform. So that is what we will be using. But if you're set on using TestLab Classic, just know that there is also an application to make this kind of estimation. This is the workflow we'll be going through, but I won't present it because it's time to just show you in the software. So what I have here is a TestLab project, and what I want to actually start with first is the preparation phase of measuring mount stiffness. I won't be measuring live here. We don't have time for that in the webinar anyway, so I'll be using a ready-made measurements, but I'll take you through the different steps that we went through to get to the final results. What you can see that we've done here is using a new workbook in TestLab Neo, which is called Virtual Instrumentation. We can load in a virtual geometry representing the test setup that we want to measure on. Using this Load CAD button on the top, you can see that I've loaded in some JT files. So these are, in this case, actual CAD models of the mounts and the jigs that we use for the measurements. But you could also use something like an FE mesh or a geometry scan mesh if you don't have access to an actual CAD. This is the virtual geometry that we want to measure on. And the reason for loading in this geometry, by the way, is because this makes our life so much easier when it comes to performing virtual point transformation. So what I need to show you is that, yeah, we have our jigs. Maybe I'll just remove them so that you can see the mounts. The actual mount that we want to characterize is this one. So it's a small powertrain mounts. And what we've done in this virtual instrumentation workbook is we have defined 2 virtual points, which are these green points exactly at the center of the mounts. Now, if I highlight them, you'll see that there are in fact 2 different ones, but they are located at the mount center. So we're basically modeling our mounts as a points connection between the active and the passive sides. But depending on the virtual point that I select, you'll see that the instrumentation on the 2 jigs is swapped. So the active side virtual point is calculated by transforming the FRF data we measure on the top parts of the mount, so the top jig. And then the passive side FRF data is estimated at the same physical location, but based on the FRF data coming from the bottom jig. And these jigs are just something that we manufacture them ourselves in our workshop. So this is something that we do optimize typically in CAE where possible to find some geometry that gives us the highest rigidity. So the highest frequency for the first bending modes is something that we optimize in CAE. And then we manufacture them in our workshop because they need to fit exactly on the geometry of the mounts that we want to measure. Now, the reason for preparing the test like this with virtual instrumentation is that it will allow us to do some validation work before we even start measuring. That is what these green cells at the bottom are doing. This is a validation window that allows us to see whether we have enough measurement data. So did we put enough acceleration degrees of freedom, enough excitations to estimate 6DOF data at the virtual point? And these condition numbers are there to then also tell something about the geometric distribution. Basically, when these condition numbers become orange or red, it's telling you that you're missing some degree of freedom in the estimation. I think for PCB, well, don't shoot me if I'm wrong here, but I think they have these sensing elements at the center. And that's also why when you take one of these sensor models from the TestLab library, so everything you see here is delivered by default with TestLab. You can add your own sensors later if you want, but we make sure that we apply an offset to where the actual sensing takes place. A small offset in where the actual sensing takes place is relevant for virtual point transformation because it changes the moment contribution at the virtual points, for example. We have been adding support for additional file formats over the last releases. So it used to be only PRT and JT. With the last release, we also have STL, STEP, and these other ones that I've never used, IGS, Creo, SolidWorks, IFC. Yeah, so what I wanted to say is these conditioning metrics are calculated on the fly. So if I start doing something like modifying my test setup like this, so I reposition two of the impacts to a different location, you'll see that suddenly the condition number for the references or the impact positions has increased to 67, which is a bit higher than we would like for an accurate estimation of the 6DOFs. In my detail tab, I can break this down into the actual individual degrees of freedom, and you can see that now it's a bit higher. Why? Well, the two worst performing degrees of freedom are the Y degree of freedom and the RX. So based on that result, I can think like, okay, maybe I have to put an excitation along this degree of freedom to more accurately and more precisely excite the RX degree of freedom in the virtual point. That's a capability that I think is really nice, that you don't have to do the measurements in order to find out that you missed some degree of freedom. You can just already make this prediction and optimize your test setup before you even do one FRF measurement in the laboratory. Once we've done this, next step is the instrumentation parts. I won't be going through every single step like calibration and so on because it's not so interesting. What I think is interesting is this geometry lookup tab. And what we can do here is basically on the left, I have the channels of my front ends that I'm connected to, and I can basically say, okay, the first 9 channels I'm instrumenting now on the front ends. And then I can just take my model and say, okay, these 3 accelerometers, those are the ones that I want to attach to channels 1 to 9 in that order. And when I hit this assign to channel button here, what will happen is TestLab will synchronize the naming convention from the virtual instrumentation, but also certain properties like the conditioning or the sensitivity that is typical for that sensor from my sensor library. And the goal here is just to make sure that when we actually go for the measurements, that the measured FRF data is matched to the virtual instrumentation, such that we can use the virtual instrumentation to also perform the VPT calculation automatically. My setup is already made here, so I don't have to update the channel setup, but this is where I would try to match the physical and virtual setup to each other. Next step I want to look at is the impact setup. So we are using impact testing for this. Of course, you can also make use of shaker testing if you prefer. And we're using one hammer here. So we did these measurements with the metal tip hammer that gives us data up to about 10 kilohertz, maybe not quite 10, but you'll see later, it does give a very high frequency range. Depending on the mount that you're measuring on, that might not give you enough excitation energy on the low end. for some mounts, it might be beneficial to actually define a second hammer, like a plastic or maybe a rubber hammer for the really low frequency range, and then do something that is new in TestLab, which is the ability to merge the data from multiple excitation sources automatically. So here we're defining a cross filter, so a high pass for the metal hammer, low pass for the rubber, and then later, whenever we're doing any measurements on the mounts, TestLab will automatically preserve the low frequency content from the rubber tip and the high frequency content for the metal tip. And that just allows you to distribute your excitation energy a bit better over the frequency range. Now, in this case, we didn't do that, so I only have data for one tip, so I don't need to apply any kind of filtering here. Next step is the campaign setup. In the campaign setup, we can define the order of the measurements. If you really don't want to be next to your laptop, you can just predefine exactly which impact should follow after which other impacts. In this case, we build it up completely automatically from the virtual instrumentation. And what you can see is that this is a pre-measured data set. So I already have some impact data available, around 10 impacts per point for all the degrees of freedom on my virtual instrumentation. Very briefly on the measurement parts, the measurement itself works like this. So at the bottom, I have my virtual instrumentation. Again, I can visualize, okay, which points am I supposed to impact? So if I start with the first one, to acquire data here, I need to impact on that location of my virtual instrumentation. And then as I'm impacting on the jigs, the measurement data will be collected for that point. So you can see that we now measured 10 impacts on this point. And I can look at the individual impacts. So they are shown on the right in red. And the green results are the average results for the entire measurement. And something that I really want to highlight here, because again, it makes a big difference on the frequency range and the validity of the results, is a question that everyone struggles with impact testing, which is, when can I stop impacting the structure? So when do I have enough impacts to have good data quality in the frequency range of interest? Mostly, we're using rules of thumb, like at least 5, maybe up to 10, and you should have enough good data in that data set. But in reality, you might be just having a bad day, or you might be getting tired, and maybe 10 isn't enough. Maybe you actually need 20, or maybe you did a really good job and you can actually already stop at 5 impacts. You don't have to do the 5 extra to get up to 10. That is exactly the situation where this next feature will come in, which is what we call smart hit selection in the software. So this is a new capability where if I hit this checkbox, then after or even during the measurements, TestLab will automatically select which impacts need to be kept in order to optimize some quality metric. So we can either optimize the similarity of the everests or the coherence. It doesn't really matter all that much, but for VPT, I like to work with the similarity of the individual everests. So what TestLab will do is between 200 and 4,000 hertz in this case, we're trying to get up to 95% similarity between the individual everests and the averaged results. So we're only keeping the everest data that fulfills that condition, but we want to have at least 5 impacts to have enough spread in the average, and we don't need more than 10. So if we have 10, the software can tell us to just stop the measurements, we can go to the next point. And if we apply that strategy to, in this case, this 1 point, what you'll see is that now the number of selected impacts is 5, so the minimum amount that I specify, and I get up to 99% similarity with that selection. So to get this, we had to exclude the first 4 measurements and then this one. So in the beginning, we were just warming up. The data quality wasn't great, but these last 5 or 6 impacts were a lot better, and they contribute to a more consistent impact testing results. And what you'll find is that in general, this algorithm is very good at identifying bad quality data. So like here, for example, why was this measurement now excluded? Well, the actual excitation energy was quite a bit lower than the average one in green. We probably hit the structure a bit softer than we should have. Maybe I can show the peak force level is only 61, which is the lowest of the entire data set. And that also means that my response data will be just a bit more noisy compared to the other measurements. Also in the everest data, you can see the average result in green, and then this around this anti-resonance on the excitation spectrum, you have quite bad data quality for that measurement, so it gets excluded. And we're doing this for 1 point, but this algorithm is actually working automatically across all the response points of the measurements. So this is something that you would never be able to do it as quickly by hand as letting the computer essentially figure it out. Now, why I'm saying this is because this is a really great assistance during the test to get the best possible data quality, but also make your test more efficient. So now I'm doing this point by point, but actually the best way to use this algorithm is just during the measurements, allow the software to tell you when you can stop impacting, when should you go to the next point, or when you maybe need to exceed the planned amount of excitations to get a certain data quality. So maybe you need to go from 10 to 15 or 20 impacts to get the best data quality. Yeah, once we apply this algorithm to the entire data sets, we basically get the best selection of impacts to get the most consistent FRF data quality. And again, that is something that is going to pay off later during the VPT when it comes to the frequency range. If I hit this floppy icon on the bottom, I can actually save the results for my impact selection to the project, and I can get started with the virtual point transformation. I have in my project here a folder that contains these results. So this folder contains the impacts processed with an optimal selection of impacts for each point. And I'm going to collect those in the input baskets. And now we're going to perform the virtual point transformation. So in this PPT workbook, I'm going to load in my data from the input baskets. I can do some inspection of the FRF data here. So you can see these two blocks, if you want, in the FRF matrix are essentially the FRF data on the active to the passive sides. And then off diagonal, you have the cross FRFs, which are logically much lower. And because this is a lot of FRF data, it can be useful to have this kind of view, like saying, okay, in the frequency range of interest, let's say 200 to maybe 3000. What does the coherence look like to identify some weak points? Like here, I have a point that is maybe not performing as good as I would like. Coherence isn't too great in that frequency range, but if I look at the CAD data, I can see that it's because we're performing measurements on the passive side and we're measuring the response on the active side. So actually, there is a lot of decoupling happening between these degrees of freedom. So this result is still acceptable from my point of view. Okay, so that's for the data validation. What comes next is the actual calculation itself. In this calculate window, what is important here is the type of transformation we perform. So we want to transform both the response and the reference data. What that means is that the output of the transformation will be this 12 by 12 FRF matrix at, but also between the active and passive side virtual points, which use 6 degrees of freedom each respectively. And what we also want to do is to check this box for calculate bound stiffness. So this is actually implementing inverse substructuring on that FRF data. And we need to specify what is the input. So what is the active side of the mounts? It's my active VP, and then the output is going to be the passive side's virtual points. With that, let's run the calculation. In the background, what TestLab is doing is it's taking the virtual instrumentation, and then based on the positions of our measurements from the CAD model, we can automatically apply this transformation. So this kind of happens automatically based on that preparation work that we did before. My frequency range of interest is going to be somewhere from 200 to 3000. That's more or less where I think we can reasonably get good results. The FRF matrix that we calculate is this one with these crosses that you see. So that's the typical pattern that you will find in this kind of measurement data. And the part that is interesting for us is this top right, but also the bottom left matrix, which are the off-diagonal parts. So this is where all the transfer properties are stored. Now, how do we know if this is a good transformation result and up to which frequency that we can trust those results? For that, we have to switch to this validate view. And the main metric that I want to focus on here is going to be just one of the two. So there's a lot to say about VPT validation, but for time reasons, we're just going to focus on rigidity. So rigidity is actually a metric that, as you can see, it calculates similar to a coherence function. It's between 0 and 1, and it validates whether the measured data follows the assumption of local rigidity that is essential to VBT. And rigidity tends to start at 1 or 100% at low frequencies, but as we go to higher frequencies, we start to have more local flexibilities in the fixtures or inaccuracies in the sensor positioning, which starts to reduce the rigidity and also the validity of the results. Now, the rigidity for my passive side estimation up to 3 kilohertz is pretty good, actually. Maybe I should increase it a bit more even to make the story better, like this. So let's say that we want to get mount stiffness up to 4 kilohertz in this case. The overall rigidity for that frequency range is summarized in this table. So you can see that for the passive side mounts, we are at about 98%, which is a really good result. So we did a good job on the data quality. But for the active side mounts, if I select it, we're only at around 80%, 84, which is not really as high as we would want. And if we look at the rigidity for that virtual point, we can see that it starts to drop off earlier than before. So maybe up to 2 kilohertz, maybe 2.5. That's the maximum range where the virtual point transformation is valid. Now, the reason why this happens is it can be because the structure, the jigs are not made rigid enough, but what is also possible is that we didn't do a good job of pasting our accelerometers exactly where we said they would be on the CAD model. So there is kind of a mismatch between the virtual and the physical instrumentation. Now, we could imagine remeasuring or trying to do a better job on the instrumentation, but there is another feature that I want to highlight here that really makes a huge difference on the frequency range that we can achieve, and it doesn't require any remeasurements, and that is to simply optimize the selection of the sensors for the transformation. By default, the worst rigidity is here on the responses, so if we check the responses first, you can see that by default, we are performing the transformation with all response degrees of freedom. But in reality, maybe some of these accelerometers are mounted on locations with local flexibility, or maybe one accelerometer was badly positioned on the structure, and that is the cause for the weak rigidity. So in reality, what we want to do is we want to optimize the selection of which data is now going to actually be used for the transformation. And you can do this by hand using the correlation error tables, but TestLab also has the ability to do this automatically for you with this automatic indicator selection button. What this does is it brings up this window where we can see that, okay, we have 15 degrees of freedom of response data to start with. Let's maybe throw out 2 of the 15. So the 2 worst performing degrees of freedom, let's just eliminate them. And whenever we throw out data, we do want to make sure that we still have enough geometric distribution on the data set that remains so that we don't miss any degrees of freedom on the virtual point. So if I hit auto select, in the background, TestLab is now optimizing the selection of which indicators give me the best rigidity performance for the frequency range that I select. So between 200 and 4,000 hertz in this case. Coming to the automatic indicator selections, what you can see is that the algorithm has chosen to throw out the X and Y degree of freedom of the same triaxial accelerometer. Very likely what is happening here is that accelerometer 5 was maybe misaligned in the actual physical instrumentation, and it might be better to just remove it altogether from the data sets. So now we are already up to 87%, so almost 90%, which is the rule of thumb threshold that we would like to achieve. But if I additionally throw out the last degree of freedom from this triax, so we're not using accelerometer 5 at all during the transformation, now we're up to 91% rigidity from 200 to 4,000 hertz. And that's the rigidity range where we would like to end for our frequency range. You can go on optimizing this because ideally you would also repeat that exercise for the references and maybe also for the passive side virtual points. So you can spend a bit of time, but TestLab really does help you to find the optimal selection using this automatic indicator selection algorithm. I've already gone through the efforts of doing that selection to really get it as good as we can for these particular data sets. And then I saved my VPT results to my projects. And because we hit the estimate mount stiffness checkbox, we also get this mount stiffness folder. Maybe first what I can show you is on the validation part. So for the rigidity, if I just plot the rigidity, and let's not cheat by putting it in dB, so amplitudes between 0 and 1, you can actually see for all excitations responses which rigidity we got from our data selection. And if I add a cursor here, you'll see that the frequency where rigidity starts to really drop for many of these points is at about 3000 Hertz. Based on the design of the jigs that we have here, mount stiffness is going to work up to 3000 Hertz, you could say, and above that, we might need to be a bit more careful in trusting the results. But this is already a very, very high frequency range when we think of the typical frequencies where powertrains are putting in significant amounts of structural excitation to a vehicle. The actual mount stiffness is stored in this folder, and it's a 6x6 matrix, as I can show you here. So we are actually storing that off-diagonal part, that 6x6 parts of the inverted EverF matrix, if you want. And you can see the individual mount stiffnesses on the left. So for the translational degrees of freedom, it's in Newton per meter, Newton per millimeter. Doesn't change the curve, of course, but this is basically the dynamic stiffness that we estimate, which at low frequency, I don't really trust the results because the EverF data quality is maybe not optimal there, but we can use these results probably relatively confidently up to maybe 3000, 3200 before the VPT starts to break down. And again, it's not just the principal degrees of freedom, it's 6x6. So we have the full coupling complexity for higher frequency applications like here, 3000 Hertz. You can see that some of the off-diagonal contributions are significant at higher frequencies. This kind of cross-coupling starts to become important when we consider the assembly dynamics here. Okay, well, I hope that was interesting to see how that works in the software. Okay, thank you.